Hello, friends. So binary is great for computers, but for humans, reading long strings of zeros and ones gets messy real fast. That's where octal and hexadecimal come in. They're shorter, cleaner ways to write the exact same binary value. And the best part? Converting between them isn't math-heavy at all. It's mostly just grouping. In this video, let me show you exactly how binary turns into octal and hex, and why these two number systems exist in the first place. All right, before we get into the conversion, let's quickly answer a fair question. Why do we even need octal and hex? Look at this binary string on the left. It's just a few bytes of data, but already your eyes are struggling. Now imagine debugging a memory dump or a crash log filled with thousands of these. Painful. Octal and hexadecimal solve that. They represent the same binary value, but in a much more compact form. 3 binary digits collapse into 1 octal digit. 4 binary digits collapse into 1 hex digit. Same information, fewer characters, way easier to read. That's the whole reason these number systems stuck around. They're built for humans working with binary data. Now, here's the trick that makes this whole thing easy. Octal and hex aren't random. They're carefully chosen so that conversion from binary is just grouping. For octal, you group the binary digits in sets of 3, starting from the right. Each group of 3 becomes 1 octal digit. For hex, you group them in sets of 4, again, starting from the right. Each group of 4 becomes 1 hex digit. That's it. No long division, no complicated math. The reason this works is simple. 3 bits can represent 8 values, which is exactly 1 octal digit. 4 bits can represent 16 values, which is exactly 1 hex digit. The number systems were literally designed to line up with binary. Let's actually do this step by step now. All right, let's do binary to octal with a real example. We've got the binary number 101110110. Step 1, write it out. Step 2, group it into 3s from the right. Always from the right, because that's where your least significant bit lives. So we get 110, 110, and then just 10 left over on the left. When a group is short, you just pad it with zeros on the left to make 3. So that becomes 010. Step 3, convert each group to a single octal digit using this small reference. 3 bits can represent values 0 through 7, which is exactly the range of an octal digit. 010 is 2, 110 is 6, 110 is 6 again. Read them left to right and you get 266. That's it. Binary 101110110 equals octal 266. No calculator needed. Now let's do the same number in hex. Same binary. 10110110. Step 1, write it out. Step 2, this time we group in 4s from the right. We get 1011 and 0110. Already a clean 8 bits, so no padding needed here. Step 3, convert each group to a single hex digit. And here's where hex gets interesting. 4 bits can represent 16 values, but we only have 10 regular digits, 0 through 9. So hex borrows the letters A through F to cover the values 10 through 15. A is 10, B is 11, all the way up to F, which is 15. So 1011 is decimal 11, which is B in hex. 0110 is 6. Read them left to right and you get B6. That's our answer. Binary 1011011 equals hex B6. Same value as octal 266, just written in a different base. Now, let me explain why this grouping trick works so cleanly. It comes down to powers of 2. 3 bits give you 2 to the power 3, which is 8 possible values, exactly the range of 1 octal digit, 0 through 7. 4 bits give you 2 to the power 4, which is 16. Exactly the range of 1 hex digit, 0 through F. That's not a coincidence. Octal and hex were specifically chosen because their bases are powers of 2. 8 is 2 cubed, 16 is 2 to the 4th. So a fixed group of binary digits always maps to exactly one digit in the new base, with no leftovers and no math. Compare this to converting binary to decimal, which is base 10. 10 isn't a power of 2, so the grouping trick doesn't work, and you actually have to do real arithmetic. That's why programmers love hex and octal. They line up with binary perfectly.
Going the other way is just as easy. To convert octal back to binary, take each octal digit and expand it into exactly 3 bits. So 266 becomes 010, 110, 110. Glue them together, and you've got the binary back. The leading 0 on the left is just padding from earlier. You can drop it. To convert hex back to binary, take each hex digit and expand it into exactly 4 bits. B is 1011, 6 is 0110. Glue them together, 1011, 0110. Same binary we started with. So the conversion works in both directions, using the exact same logic. Group to compress, expand to decompress.
So where do you actually run into octal and hex out in the wild? Hex shows up almost everywhere. CSS color codes, that hash FF5733 you've seen in web design, that's 3 pairs of hex digits, one each for red, green, and blue. Memory addresses in a debugger or a crash log, those 0x prefixed values are hex. MAC addresses on your network card, IPv6 addresses, raw byte data in any hex editor, all hex. Octal is rarer these days, but it has one famous home: Unix file permissions. When you run chmod 755 on a file, those 3 digits are octal, and each one expands to 3 permission bits for read, write, and execute. So next time you see chmod 755, you now know exactly what's happening. 3 octal digits, 9 binary bits, 3 permissions for 3 groups of users. Not magic, just grouping.
All right, quick recap. To go from binary to octal, group your bits in 3s from the right and convert each group to 1 octal digit. To go from binary to hex, group your bits in 4s from the right and convert each group to 1 hex digit. Always group from the right, and if the leftmost group is short, just pad it with zeros. Leading zeros never change the value. And remember the deeper point. These conversions feel almost too easy because octal and hex were literally designed to align with binary. 8 is 2 cubed, 16 is 2 to the 4th. That's the whole reason you're not doing real math here, just regrouping. Once that clicks, hex and octal stop feeling like extra number systems to memorize and start feeling like what they really are, just shorter ways to write binary. And that's binary to octal and hex. Once you see it as grouping instead of math, the whole thing just clicks. If this video helped, drop a like and subscribe. It genuinely helps the channel grow, and there's a lot more computing content on the way. Got a topic you want me to break down next? Tell me in the comments. Thanks for watching, and I'll see you in the next one.